In this talk, we present a new solution for training the low-precision network with a full-precision auxiliary module. Network quantization aims to map the continuous weights and activations to discrete low-precision values for efficient bitwise operations. However, training low-precision networks can be difficult due to the non-differentiable quantization function. To solve this problem, our motivation is that since full-precision networks are easy to be optimized, we create full-precision rules to update parameters of the low-precision model, and thus alleviating the difficulty of propagating gradient in a quantized model. To avoid introducing additional complexity, we propose to introduce the weight-sharing strategy. Now we give an overview of the framework. The blue part, denoted as F, shows the low-precision network we aim to learn. The pink part, denoted as H, is a full-precision subnetwork, which we call the auxiliary module. It connects to intermediate outputs from F. At the training time, we combine F and H to form an augmented mixed-precision network, and the parameters of the low-precision network is shared by this augmented network. Then, two loss functions are applied to both outputs, where the mixed-precision network and low-precision network are trained jointly. After training, the auxiliary module H will be discarded, and only F will be used at the test time. We now elaborate the design for the auxiliary module H, which is made up of a sequential of adapters and aggregators. Formally, the pth aggregated feature is obtained by adding the adapted feature from F and the previous stage aggregated feature from H. To investigate the effectiveness of the proposed method, we first evaluate the proposed auxiliary module on ImageNet classification. We can observe a steady performance increase compared with the original baseline. It's worth noting that when the network becomes deeper, the improvement turns out to be more obvious. We also plot the convergence curve, which shows the auxiliary module makes the convergence faster and better. We further compare with other related approaches, including knowledge dissolution and adding auxiliary classification losses to intermediate activations. In terms of adding additional losses, its supervision is very restrictive, since it essentially assumes that the intermediate output can be directly used for classification. Also, there are many advantages of our method comparing to knowledge dissolution. First, our method only needs an actual memory to store the auxiliary module rather than a complex, full-precision network, which is more memory efficient. Second, our method only uses a single auxiliary loss, but can create guidance signals to hierarchical blocks of the low-precision model. In contrast, knowledge dissolution needs multiple dissolution losses to achieve this. We empirically find that the proposed learning strategy performs consistently superior than these related approaches for learning quantized networks. We apply our learning approach and propose a new design modification to build a 4-bit quantized object detector, which achieves comparable performance to its full-precision counterpart. We claim that the detection heads should not be shared in the quantization scenario. Specifically, the batch statistics of quantized activations may differ drastically across different levels. Therefore, each head should learn independent parameters to capture the corresponding multi-skew information. The source code and pre-trained models are available. Thanks for listening.